And here we go. My most favorite symbol in all of mathematics right here. This is it. This is it. Nothing better. Nothing finer than eating in your diner. There we go. It is the following. It is that. Okay. Now, what is that? Okay, that is known as the integral sign. All right? Now, what that is that is an elongated S, a stretched out S. So you'll see some people that would go like S, or they'll go S. I really don't care. That's the symbol. One of the popular references to this is the sound hole on a violin. How many of you know what I'm talking about? Sound hole on a violin. It is so popular that a very famous mathematician who wrote many of the textbooks used by the University of Regina, that is his symbol on the textbook. Okay. And for different editions of it, looks different, but it, yeah. The man's name was James Stewart, and the house that he designed was actually called the Integral House, believe it or not. Look it up. Okay. No.
Do you want to go there?
No. And he didn't invent the symbol either. But guess who did?
Leibniz.
Leibniz. And in fact, when you look at Leibniz's picture, you will see superimposed on his picture what I've written right there.
Oh.
Yes. So, tip of the cap. And here's the thing. We don't even show people Newton's notation because it was that bad. And nobody else has a better one. There isn't another one that represents, hey, take an antiderivative. Not one. Leibniz's is the only one that you'll see in every book. So you know how there's prime notation and dy over dx and all that kind of stuff? There isn't another one for this. That's the only one.
What did Newton's look like?
Oh, it was gross. It was called the method of fluxions, and it was just dots. And then he would just cross out dots. It was dumb. Not dumb, but it's not good. It's not universal. It doesn't. Whew. That being said, yes. And what that is equal to, this idea here, is it's just equal to the antiderivative. So all that expression is equal to is the antiderivative. So all the things that we've been doing, that means just take the antiderivative. That's what that means. So this symbol over here means anti-differentiate that. Okay? That's it. So it consists of parts, and the parts are important. The first part, the integral sign. The function that we are anti-differentiating is called the integrand. And the little dx at the end, that is what is called the variable of integration. And that right there is the general antiderivative of f of x. So beautiful.
When do we start putting numbers on the integral sign?
Ah! How much time do we have left today?
Oh no.
9 minutes?
It's 12:05.
Oh, Friday. So, a couple of rules. And there's only two that we actually need in order to really devour these topics. The first one here, which is called the constant rule, is this, that if we take the integral of a constant times some function, okay, So if we're integrating a constant times a function, as long as it's a constant multiple, what we are able to do is actually take the constant out in front and then just integrate the function. Okay? Now, that rule doesn't really seem that valid or important, but it is something that we are able to do. That constant multiple, we can just take the constant out. Doesn't have to be involved in the integral. The other rule, which is the sum and difference rule, is that if we have a function plus or minus a function, like that, then what we are able to do is we are able to integrate each function separately. Now, integrate is just a fun word that just means antidifferentiate. So an integral is the notation of antiderivatives. That's kind of how we're looking at this, okay? Now, theoretical mathematics is going to argue with what I just said right there, and they are right, okay? They are related, but they're not the same. But the way that we are going to think of the integral sign is as take the antiderivative. That's how we are going to view that. Take the antiderivative. And all it is just a notation to do that. That's it. That's it, that's all. So let me show you how to do that. So let's evaluate the following. They always use that word when you take an integral, whether it be an indefinite integral like what I'm showing you right now, or a definite integral like what I'm going to show you on Friday. Because like I said, the majority of your class time tomorrow is just a work period to just get good at antiderivatives. I know. Would you like me to give you the booklet today? Sure, good, I thought so. So let's say that we have the following. The integral of 3x dx, okay? So all this is saying is, hey you, antidifferentiate 3x, okay? Well, the antiderivative of 3x is just 3 times the antiderivative of x. Well, what's the antiderivative of x?
1/2 x squared.
It certainly is. Plus c. So, when you compute the antiderivative, the integral sign and the variable of integration go away. Just switch your left. Just like that. Ah! Yeah! Number 2. What if I have the following? X plus e to the x dx. Ooh. Well, if we have the integral of x plus e to the x, well, we're adding functions. So what the rule says is we could just integrate each one separately. And integrating is just the same thing as taking the, you got it. So let's do it each separately. The antiderivative of x.
1/2 x squared.
1/2 x squared. The antiderivative of e to the x. And let's not forget that good old plus c. We're going to make that symbol like possibly 1,000 times in semester 2. So good. It feels so nice when you do it too. It actually doesn't feel bad with the marker. It felt better with the chalk, but it's not bad. Now, let's imagine that we have the following here. X times 3x minus 5 dx. Whoa. What do we see here? A product! And what can you not deal with? You can't deal with products. What can you only deal with? Sums and differences. So if it's not a sum and difference, guess what we got to do? Make it a sum and difference. So because we are using a step, we rewrite the integral sign. And I'm going to use a nice square bracket here to contain everything that is now going to remain. We multiply through x times 3x. X times -5. Now, after that expansion, we are dealing with a difference. Can you integrate a difference?
Yep.
You know you can. And here we go. The antiderivative of 3x squared. Well, that's going to be 3 times the antiderivative of x squared, which is?
1/3 x cubed.
It certainly is. Today and every day. Subtract 5 times the antiderivative of x, which is?
1/2 x squared.
Plus, of course, the arbitrary constant c. Giving us x cubed minus 5/2 x squared. Have you ever had more fun?
No.
There it is.